Welcome back to our lecture video. We will now begin with chapter 8, starting a new discussion on what we call the inferential statistics. And in fact, chapter 8 is a fairly short chapter, but nonetheless it contains a very important concept and introduction to the idea of inferential statistics. So you can see here in our chapter 8 we only have two sections to study. The first one is the sampling distribution of the sample means, and the second is the sampling distribution of the sample proportions. Now, up to this point, we have studied quite a number of distributions already in statistics, particularly if you recall from the last few chapters, starting with chapter 5 and 6 and 7. And let's just take a moment to review these individual distributions so that we can get a better understanding and idea, so that we can use that and then move on to talk about a distribution presented in this chapter, which is chapter 8. Okay, so I'll just list a number of the distributions that we have studied. So here we have studied the discrete probability distribution. Oops, that's not discrete. Let me discrete probability distribution. That we, if you remember, that we call the expectation value or expected value. Okay, that has this expression. And this expression, if you recall, it was derived directly from a mean value equation. Okay. The next distribution that we studied was the binomial. Probability distribution. Which has this expression. Actually, this is a longer and a dot line, and so let me make that clear. Then we have the probability of success raised to the power of the number of successes, and the probability of failure raised to the power of the number of failures. And if you remember, in here, let me put it this way. So here we, using the binomial probability distribution, we were able to compute a probability of exactly x equals 2. And you can see here, this is an individual number that we computed for x exactly equals to 2. And we also look at computing a range of values, such as, for example, let's say a number of success that occurs between or occurs at most up to 2. So here you have to compute a range of values starting with p of x equals 0, x equals 1, and then x equals 2, and then you can add them up to get the range of those values. But the underlying principle of this calculation is that we individually computed the value for individual x, and then we just add them up, right? And you could also do this by using another expression, and we did quite a number of that in the example that I provided in my lecture. But my point here is that all of these are basically a way to compute an individual number or a variable within a group of data, and that's my point here. Now we also looked at a general and uniform distribution, and the one that we looked at was the Poisson distribution, which has this expression. Where E is the exponential value, which is 2.71828. And again, you can see here that this Poisson distribution, we can use it to compute, for example, let's say, x equals 3, or x is at most 3, or x is less than or x is greater than 2, or something like that. And you can see here all of these again are dealing with a computation of individual values. And then the last distribution that we looked at was a normal distribution. Normal distribution that has this expression. Now the normal distribution, basically you can see that we looked at using by comparing the general normal distribution that has this bell-shaped curve with an arbitrary mu value, and then let's say a standard deviation sigma to the left or to the right of it. And we look at computing the general distribution by converting it to the standard normal distribution by using this equation that we call the z-score. Okay, and so using that equation we are able to translate the general normal curve to the standard normal curve. So this is what we call the standard normal curve. The word standard is very important because these two are both normal, and in fact I noticed, I gathered that quite a few people expressed their opinion about their struggle with the conceptual understanding of the definition of these distributions. For example, the difference between the general, this is what we call the general normal curve, and then the standard normal curve. So the similarity between these two, you can see that they have the normal curve. That's why we call the normal curve. All right, and the reason why we call this general, because this curve kind of have an arbitrary value of the mean. So the mean value here can be an arbitrary number. It could be anything, and with the mu equal anything, the sigma can also be anything. So this is why we call the general curve, which has the symmetric curve. The standard normal curve has the same symmetric curve as the general, but it has a different property, that it is now standardized with the mean value equal to 0 and the standard deviation is always 1. Okay, so that's the big difference between these two, and the similarity is that they obey the empirical rule, meaning that they have the normal curve distribution. Our key here is this, that you see, even when we look at, this is what we mean the continuous distribution, because it is a continuous curve, is that when we look at a problem, if you remember back in chapter 7, we computed a probability of, again, x equals a certain number, right? X here is basically based on a certain number. Let's say, for example, let's say x is less than 82 or something like that, or x is between, let's say 2 and 6. So at first glance you might have thought that, okay, well, this one here contains a set of numbers, so therefore it looks at a bunch of numbers at the same time, but clearly it's not. You see here we compute the x value based on individual. So here you have a 2, 3, 4, 5, and 6 range of values to be computed individually, and then we can add them up to get a range of values for the probability. But the point is that we look at, up to this point, all of the distributions that we have studied, we only look at computing an individual value, an individual variable, a single value selected from a group of data. That's my point here, to take the past several minutes to review that for us. Now, in this chapter and the next several chapters, we will deal with inferential statistics, as I mentioned earlier, and for this branch of statistics, we require not a single value or variable, but a set of variables selected from a group of data. So let's write that down. So here we have chapter 8, and of course the next several chapters. Okay, we deal with inferential statistics. That's the second branch that we were introduced back in chapter 1. And for this particular branch, we require a set of samples. Okay, we require a set of samples selected from a group of data, and here the set of samples will produce a sampling distribution. That's the key here. So a set of samples will produce a sampling distribution. I'm going to abbreviate the word distribution here, and this is the key in this chapter right here. Okay, so here, by obtaining a sampling distribution from a set of samples, we can study a group of numbers or variables at the same time. Okay, so I have a bunch of numbers that we can study at the same time, and the sample is the key here, and that means that we're going to look at the mean value, or mean values to be exact. Okay, now the big question then is, why do we need a sample? Well, if you remember, the answer is that it's quite simple. That is, because the population is too large and too costly to collect information, we can study the population by sampling it. That's the most important aspect in statistics, that we don't have to go around and collect the entire population. We can just sample the population to conduct our study. The most important goal in sampling a population then is that we have to somehow obtain a sample that it must be representative of the entire population. So the samples must be representative of the entire population, that it must reflect the characteristic of the population. So that is the most important element in the process of sampling the population. This means that we must carefully conduct a method to collect our sample, and that's probably one of the most crucial ideas that we need to learn here. So the big question now is this, that okay, so if we collect a sample from a data, and let's say it does not represent the true population proportion or population mean in this case, what happens if a sample is not representative of the population that we want to study? What happens if it is not representative of the entire population? Well, the simple answer is that it yields the wrong conclusion. That's the key here. So I like to mention a few words by giving you this one example about the 1936 presidential election between Alfred Landon and Franklin D. Roosevelt. And there was during that time there was a magazine company called the Literary Digest, and that company was quite successful at predicting. They were quite involved in the political research and quite involved in political elections, and they were quite successful at predicting the election outcome for almost 2 decades, starting with I believe it was 1916 all the way to the pre-1936 era, and so they were quite successful. And so during the 1936 presidential election, they embarked on a new project, and they sent out 10 million surveys, and they obtained 2.4 million surveys return for analysis. And they proudly predicted that Landon, that the presidential candidate, Republican candidate, would win the election by 57 to 43. So Landon would get 57 votes, and Roosevelt would get 43. But the actual result was that the result of the election was that Landon lost to Roosevelt by 37 to 63. So that was a huge landslide. And the result was a major embarrassing blow to the Literary Digest, because they failed to predict the actual outcome, and they did actually proudly announce their result. And so that was a major embarrassing blow. Now the question then is, how could they reach the wrong conclusion? That's my point. And especially, they had 2.4 million responses for analysis. That's a huge sample, because at the same time, a small group led by George Gallup, they were successfully able to predict the election, the outcome, and they had only 50,000 of data points to work with. So that's a small percentage to the 2.4 million, and yet they were able to correctly predict the election. So the question now is, what went wrong with the Literary Digest, the analysis and the prediction? There were a lot of people who have attempted to explain this very question, and some of them came with speculations that the Literary Digest method was flawed, simply because survey that the Literary Digest used was based on voluntary, and that is true, because you can see here that they sent 10 million surveys out, only 2.4 million return. So that means that this means that those who didn't care, they didn't care to send back their response, and those who care so much about the vote and about their opinion, they took the time to respond to the survey and send it back. So the 2.4 million were the ones who actually were involved in the actual election, or their opinion was quite strong in terms of who they wanted to elect. And also, there were claims that survey was selectively sent out based on the phone books that the Literary Digest obtained, and then based on the subscriber list, those who subscribe their magazines. And remember, this is a time during the Great Depression, and those who were able to subscribe magazines and own a telephone, telephone was a luxury during that time, not a necessity like nowadays. And so they were the do-well people at the time. And history showed that the do-well people tend to vote Republican. So here you can see here a clear bias selection, the survey that was flawed based on the Literary Digest. And also, survey selections were done, basically were not carefully designed. And if you remember back in chapter 1, you can see here that the that the Literary Digest company selected data based on the list that they made, and so they failed to classify the different groups that they need to survey, they need to collect data from. What I'm trying to say here is that their survey selection were unrandomized, unstratified, and even unclusterized. So they just collect data that purely was not statistics in nature. And that's my point here. So you can see here there's a good reasonable cause for failure, and huge sample does not really guarantee that you get the right result. And clearly it shows that they did get the wrong answer, and they did get the wrong conclusion. And this is also one of the, I would say that this incident gained what is called, the infamous place in the history of survey research. And so we use this as a great example to study statistics and to basically discuss what is in this chapter, which is chapter 8, that talks about how to carefully collect a sample from a population. Okay. Now the George Gallup group, when asked, they actually never actually described or disclosed their information how they successfully predicted the 1936 election, but they did insinuate that the prediction, that the process was through a sampling distribution analysis. So it's clear that they are using the method that we will be discussing in this chapter, which is chapter 8. Now, so the whole idea then is, in order for the data to be representative of the population, we must collect a number of samples of the same size from the same population to conduct analysis. So let me state that one more time. That's a very important statement. Okay, so that's a key here in the sampling distribution, that in order for the data to be representative of the population, okay, we must collect a number of samples of the same size from the same population. So here we'll basically collect a bunch of samples with the same sample size from the same population to conduct our analysis. That's the key in a sampling distribution technique. Okay. So now let's us list the characteristic feature of the sampling distribution itself based on this statement. So here we have so here features or properties of sampling distribution. One, there are actually two of them, and they're kind of linked together. One, a sampling distribution is a probability distribution I'm going to abbreviate this, a probability distribution that is formed when we repeatedly draw a number of samples of the same size we call it n, remember, from the same population. So that's the first property. The second property is that if we compute the samples that we collect, right? If we compute the samples, okay, for their means. So here we have a bunch of samples, and so we can compute the sample means, and we will have a bunch of sample means for their means, and construct a histogram of their means. Construct a histogram of their means, you know, all of the sample means that we obtain. Then the histogram will tend to assume so here we have a histogram that will tend to assume, oops, to assume a bell-shaped normal distribution. A bell-shaped normal distribution. You see here, recognize the keyword normal distribution. So graphically, this is what it looks like. So let me construct the layout of these two properties graphically for us. So it looks something like this. Basically, we have, so here we have a population, right? Let's use a Venn diagram to study this. So here we have a population that's something of this nature. So here we will repeatedly draw samples of the same size from this population. So let's say we draw, let's say we draw 100 samples. So here this is sample number 1. Okay, so sample number 1 contains, let's say, 50 data points. So here I have n x of 1, x of 2, x of 3, all the way to x of 50. Okay, then I have sample number 2. Let's forget about the word sample, but just write number 2 here. So here I have also x of 1, x of 2, x of 3, all the way to x of 50 again. And here I have sample number 10. Okay, and in sample number 10 I have x1, x2, x3, all the way to x50. So here, these three samples, we have 50 data points in each. And then we just repeatedly take all the way to 100 samples. So let's say this is sample 50. So then in sample 50 I have x1, x2, x3, all the way to x50, and then all the way to 100, right? So here again, within the sample 100, I have x1, x2, all the way to x50. So all of these are 100 samples. We have 50 data points each in it. Okay? So the question now is, how do we compute the mean value of the sample? In other words, how do we compute the sample means? Well, for sample number 1, we have, which is call it x1 right here, okay? That's going to be x1 bar, and it's going to be x2 bar. So my x1 bar is actually this. I have x1 plus x2 plus x3 all the way to x50 divided by 50. Okay, my writing here is it's very hard to read, but I hope and believe that you've heard and understood what I was saying. This time I'm going to write a little bit more clearly. So here, let's say this is sample number 2. Okay, for sample number 2, I would have x bar 2, and that basically contains x1 plus x2 plus x3 all the way to x50 divided by 50. Now, by the way, I want to mention that this x50 right here is not the same as this x50, okay? Because this x50 is actually from this one, and this x50 is actually from this one. So it's from the individual data. They may be different or they may be the same, we don't know. But they have their own data points. That's the key. That's what I'm trying to say here. And then if you carefully compute this, you will see that we can go all the way up to sample 100. And I'm going to just call it 100, and that's going to be x100 bar equals, again, x1 plus x2 plus x3 and so on all the way to x50 and divided by 50. Okay, and the key now, the second property claims that if we construct a histogram, it would provide or tend to produce a normal distribution. So this is a histogram. So here this would be, let's say x bar number 20, and this would be x bar number 18, and this would be x bar number 49 or something like that, and this would be x bar 30, x bar 40, x bar 60, x bar 62, x bar 70, x bar 75, 10, 12, 14, 1, 6, and so on. So you see here, it tends to produce a normal curve with the center presumably to be the mean value of the sample means. Okay, and that's the next key anyway. So you can see here that if we gather all of these mean values right here, so you can see here x1 bar is the sample mean of the first sample, x2 bar is the sample mean of the second sample, I forgot what this was, maybe x20, is that right? So let's say x20 bar is the sample mean of the sample number 20, and then x50 bar is the sample mean of sample number 50, and then x100 bar is the sample mean of the sample 100. So if we add all of these sample means and then divide by the number of the samples, and there are 100 of them, then we get what is called the true characteristic of the population mean, and we call that number the mean of the sample mean. Did you get it? So let's try this one more time. So here we compute the mean of the sample mean as follows. So we compute the mean of the sample means. The mean of the sample means. This mean here will be computed by adding all of the sample means divided by the number of the samples that we have obtained. And based on this example, we have gathered 100 samples, right? So then the mean of the sample mean has its name right here. We call it mu of x bar, which is equal to x1 bar plus x2 bar plus x3 bar all the way to x100 bar, because we had 100 samples, and therefore we have 100 sample means, and then we divide by 100. And here we basically call, and if you want to use a notation, it's going to be something like this. Okay. Now this 100 here could be an arbitrary number. We could have taken 200 samples, we could have taken 50 samples or 60 samples. We could have done that, and that number will be plugged in here. But in our example, we use 100, and that's why we use 100 here as a denominator, because this is the number of the samples that we have collected. Now, so what we mean is that the mean of the sample means, the mean of the sample mean, which is this one here, will truly or ultimately be the true population mean. So there you can see here. So we have mu of x bar. If you do the sampling distribution, you get mu of x bar to be representative of the population. And this is the key right here. So that's the first equation I give to you. Okay. Now the second equation is that, I'm going to sneak it under here. So the second equation is that the variance of the sample distribution, and what I mean by the sample distribution is this one right here, if you remember, right here. See that? That bar graph or that histogram is the distribution of the samples. And so the variance of the sample distribution has this expression, sigma of x bar squared is equal to sigma squared over the sample size. So this sigma here is the population mean. I'm sorry, the population standard deviation. I said it wrong. So if you square, that's a variance. Okay, so that's why we call this the variance of the mean of the sample mean, or the variance of the sampling distribution, is actually equal to the variance of the population divided by n. So to get the standard deviation of the sampling distribution, we take the square root of both sides. Okay, and I'm going to squeeze it in here. So we have the standard deviation of the sampling distribution by taking the square root of this expression right here will give us this. Now it's a very important equation, but unfortunately I want to sneak it in here, and I want to emphasize that it's a very important equation. Not only that, it is an equation that quite important in our calculation, but you see here, let me box it first, but you see here that this is the key. The square root of n here, or this n right here, okay, is the key that deals with several data points at the same time. So if you remember at the very beginning of this lecture, I said that the previous distributions that we have studied up to chapter 7, they were all dealing with a single value. The prediction that we made, the value that we calculated, they were dealing with just a single value. Now we are dealing with a bunch of variables or values at the same time. And the key here is in this square root of n. So here you have two equations to deal with now, right, for this particular discussion. Now the properties associated with this distribution is that you can see that let me start with a new sheet here with this new concept. So you see here that now we have, let's review one more time. So we have the mean of the sample mean, then we have the standard deviation of the sample mean, has this expression right here. So what I wanted to show was that this is the key, the square root of n here is the key to studying a group of variables at the same time. Now, also, we are dealing with this expression here. It implies that we are dealing with an infinite number of population. Here we're talking about, for example, let's say, surveying, let's say, a group of, let's say, 50 data points in a sample taken from the entire U.S. population. So here we're talking about some 330 or 50 million versus 50, and here we're talking about a huge number. So this expression right here, we think of the sample being drawn from a population with infinite size, okay, and with replacement. Now, without the replacement, which in many cases we will do, is that what I mean by with replacement is that you have a group of people, okay, just like that. You have a group of people, and then you select one person, you ask a question, and then you put that person back in the bin or in the population, and then you randomly select again. Chances are that you may be selecting that same person, but more likely you will not. But this is what we mean by replacement. After we select it, we took the data, we put the subject back. Now, so here we are, let me go back here. So here we're talking about n being an infinite, a huge number. Let's say 50 versus 347 million. Something like that. So that's a huge number. Now, if we look at a population that has finite size, a small population. For example, let's say a good example is something like this. Let's say, within the statistics class, with a class size of about 20 people, then we decide to sample it. So here we have a population of very small number, which we refer to as a finite size. And now we randomly select a couple of people to collect data. If we do that and without replacement, okay, we will insert a factor in here, and this factor has this expression like this. And let me write it one more time like this though. So sigma of x bar is equal to a square root of capital N, which is the population size, minus the sample size, divided the population size minus 1, multiplied by the standard deviation of the population, divided by square root of N. So this is a factor when you are dealing with a small population, and that when you draw a sample without replacement. Okay, I believe this discussion, the book talks about. Let me quickly locate the textbook where that idea mentions in the chapter. I just want to point that out so that you understand this conceptually. So let's see here. We have I believe it's 4 something. Give me a moment. Let's see if I can locate it. Oh yeah, okay, found it. It is on page 398, not 400, 398. So here it was mentioned in page in the book on page 398. Now, don't worry. We will not be considering, for most of the problems that we deal with, we will not be considering a finite population size or a small population. We will deal with a huge population. Obviously, if you have a small population that you can manage to collect the entire population, why try to sample it? To get your calculation more exact, then you just take the entire sample if the population is small enough. So in most cases, we will be dealing with huge population, and therefore we will be dealing with this equation right here, particularly this one right here at the bottom. Okay, that's my point. I want to mention that a little bit. And so the next question that I like to talk about is, what number can n be? So here's the key right here. What number can this n be? Oops. I don't know what I was writing. I guess I was trying to write both at the same time. N and what? So what number can n be? Okay. Actually, n is a very important number, and sometimes we call the magic number that decides how and when we can compute the sample mean and the sampling distribution to analyze the result. And there are two key elements associated with this n. So let me start with the first one that deals with that also is confirmed or affirmed by the what we call the central limit theorem, that if n is less than 30, so you need to pay close attention to this, and I don't believe that the book clearly states this, so you need to take this carefully, that if n is less than 30, the distribution of the data, so the distribution of the data, and that is the distribution of the population, okay, to be exact, must be, or I'm going to say something like this, must have a normal distribution. Okay, so what that means is that if we are to collect a sample, so we have, if we want to select sample here, number 1, sample number 2, sample number 3, sample number 10, and so on, let's say up to sample number 30. Oh no, I don't want to use the sample 30 because that might confuse the concept. Let's say number 40. Then you see here, if the sample that we collect, each sample here, has data that is less than 30. So let's say here, each of these 40 samples, they have 20 data points. So 20 is clearly less than 30. Okay? What that means then is that in order for these samples to produce a normal distribution, okay, the population itself has to be normal also, has to have a normal distribution. That's what this statement is claiming. That's what that means. That if you are collecting samples with sample size less than 30, and that you want these samples to produce a normal distribution, then the population itself from which the samples have been selected from must possess a normal distribution. That's what this statement is talking about. Okay? And then now the other way around is this, and that is property number 2, that if the distribution of the data or the population okay, does not possess a normal distribution, then the sample size that we require, okay, then n must be at least 30. Okay, n must be at least 30. So to avoid a skew of our data points. So what that means is that if you have a population that is not normally distributed, so this is a population not normally distributed, then the samples that you have to collect here, these samples, it doesn't matter how many, okay, they have to have sample size at least 30. So you have to collect data, you have to collect samples with at least 30 data points in order to produce a sampling distribution that has a normal property like that. Does it make sense? Okay, so these two are very important key features associated with the sampling distribution from any population. Okay, now this is clearly claimed by the central limit theorem, which I'll let you read my lecture note instead, because I don't want to spend too much time on this. I just wanted to present the key feature, the key concept, so that you can understand this and be able to answer the conceptual questions for the next exam, especially the definition questions. Okay, now let me before I show us a couple of examples, I would like to provide us a list of properties of the sampling distributions for the sample means. So properties of sampling distribution of the sample means. I'm going to abbreviate the words to make it one line. Okay, like that. One, we know that given a distribution, we can convert it to the standard distribution. So here, given, this is basically the concept we learned back in chapter 7. Given an X bar distribution, okay, we can convert it to the standard normal distribution. So we can convert it to the standard normal distribution. And we start with, for example, if you remember, the first equation I gave you was mu of x bar equals mu. And the second equation was that the standard deviation of the sampling distribution is actually sigma of x bar equals sigma divided by square root of n, where n is the sample size. And then the z-score that we now call the standard error equation has this expression. So you have x bar minus mu of x bar divided by the standard deviation of the sampling distribution. Okay. Now, if you look at this here, you look at these two right here, the one that I gave you previously. So these two equations right here, you can see here. Now, if mu of x bar can actually be the population mean, and then the standard deviation of the sampling distribution can also be written as the true population standard deviation divided by square root of n. We can re-express this equation like this. Excuse me. So now you have it. You have these three equations. Very important equation in this chapter, at least for section 1. 8.2 I mean 8.1. Now you can see I'm going to make a note here from chapter 7, recall from chapter 7. So chapter 7 we also looked at computing the normal curve, right? That's where we started our study with the normal curve, that we had a z-score that has a calculation like this, x minus mu divided by the standard deviation of the population. Now let's compare these two right here. See that? Compare them. See? Here we have the mean value. Here we only have a single value. That's what I meant by claiming that the previous distributions we studied only dealt with a single value. Now we are looking at a bunch of variables at the same time. So this is the key right here, and the square root of n here is also the key that I mentioned earlier. So I want you to take a look at these two equations and then try to understand them. You see, I don't want you to just remember the equation and try to plug in the numbers. That's not how we do statistics, and that's why conceptually understanding the equation is very important. The key element for us that most of us struggle with the definition in the last exam. Okay, so this is the difference between the z-score for a single value and the z-score for a bunch of values studied at the same time. Okay, so now let's take a look at a particular example from the book, and that will help you work on the next homework assignment. And to do that, I would like to give us the lecture video, the embedded lecture video. So in this case here, I would like to give, basically this is 10:16. Okay, so that is the video code for this lecture for 8.1. And now on with the example. So let's start with the example, and for that I'm going to take an example from our textbook to make it relevant to our homework assignment. And for that I believe I've already, let me see if I can locate it. I've already turned on a couple of, yeah, right here. So I like to take a look at number 13. Okay, assignment number 13, or homework number 13. But this is not assigned for homework assignment, and I have assigned number 14 for us to work on. So obviously number 13, once you understand this, you can work on number 14. So here is number 13. Okay, so number 13 we have answer the following questions for the sampling distribution of the sample means that show the that shown to the right, which is this, which is a curve right here. So let's draw that curve. I'm going to draw it so I can analyze it to show us. Okay. So this is a general curve, and we have 500 here, we have 520 here, and we have 480 back here. Okay, the first question is, what is the value of the mean of the sample means? So A here, we want to find out what mu of x bar is. Well, this is the distribution of the sample means. Okay, distro of sample means. And what that means that the middle value right here, that is the mean value, and that middle value is mu of x bar. Okay, and that is determined from a graph, from this graph directly. B, what is the value of the standard deviation of the sample means? Well, B again we can determine from the graph. You see here to the right it increases to 520, to the left it decreases to 480. So that means that it has decreased or increased by 20. So the standard deviation of the sample mean then can be concluded to be 20. And that is also from the graph. Okay. C, if the sample size is n equals 16, if n equals 16, okay, what is likely true about the shape of the population? Remember those two keys that I mentioned earlier? You can go back by go back to the previous discussion a couple of slides earlier in this video to refresh your memory if you did not catch it. Now, what it is asking is that if n is less than 30, what must the distribution of the population, the original population that we collected these samples from, what must it be? Well, if n is less than 30, in this case it is 16, which is clearly less than 30, then the distribution of the population must be normal. That's the key right here. Okay? So we say that if n is 16, we require, and you see here the problem did not even mention anything about the distribution of the population from which the distribution of the samples was collected from. So that's what we mean here. We need to explicitly make that statement that we require that the population be approximately normal. Not necessarily to be truly normal, but approximately normal. Sometimes we say it like that, just to have a minimum requirement, and that is that it must have a normal distribution. Or an approximately normal distribution. So that's what we mean. That's what we require. We require that the population be normal for a sample size less than 30. Okay, that is that question that we need to answer. And this answer here can be taken from the two statements that I mentioned earlier. Now let's go to the next part. If the sample size is 16, what is the standard deviation of the population from which the sample was drawn? So we are given the distribution of the sample. Now we need to compute the standard deviation of the population. And to do that, you have to apply the equation that we wrote down earlier. And that is this equation right here. Okay, so this is which is part D. So part D is this. We need to find this. And from this curve, from this sampling distribution, we already know the standard deviation of the sample means, which is 20. The equation that we need to compute is from here. So here we need to solve for sigma, right? Now I'm going to cross multiply square root of n and rewrite it so that we can have sigma is actually equal to sigma of x bar times square root of n. And here sigma of x bar is 20 and square root of n is 16. So the standard deviation of the population is 80. You see here, these questions are fairly straightforward if you fully understand the concept. Okay, so I think the video has been too long already, far too long, and I would like to make it short. So I'm going to end it at this point, and I will record a couple more to show you various examples how to apply the sampling distribution of the sample means technique to compute the standard deviation of the sample means and the mean value of the sample means. Okay, and compute the probability, the analysis of using table 5, which is the Z table that we were introduced back in chapter 7. So I like to end my video at this point and look forward to view a few of my other videos dealing with these type of problems from section 8.1. Thank you.